All right. All right. Hey, everybody. Thank you for coming. Today we've got Dr. Michele Barbato. He is a professor in the Civil Environmental Engineering department in UC Davis, and is the director of the UCD Climate Adaptation Research Center and the director of the Citrus Climate Initiative. And he's also a PE in Louisiana and in Italy. So far, his research has really been about innovative construction methodologies and materials, performance-based methodologies for different types of disasters like wind, fire, and hurricanes. Uh, he's also done research in nonlinear finite element analysis, random vibration theory, structural reliability, multi-hazard assessment under current and changing climate conditions, life cycle cost optimization, and sustainable structures for multiple hazards. A really broad research portfolio and a very impressive one. And speaking of, he's also authored over 200 technical publications and received numerous teaching awards like the ASE Mosef Award, 2011 European Association for Structural Dynamics Junior Prize, the Walter L. Hubbard Civil Engineering Research Prize, UCD Chancellor's Innovator of the Year Award, and he's also involved as a fellow in SEI, EMI, ASE, and is the vice president of EMI. So, with all that said, very excited to have you, and please take it away.
Thank you. It's a pleasure to be here today and have the possibility of presenting some of the ongoing research that we are doing at UC Davis on assessment and mitigation of wildfire risk in the wild and urban interface. I'll go directly into the topics. So after a little introduction, I will present an assessment methodology that we are developing for wildfire fragility and our research on earth block construction as a tool for wildfire risk mitigation. And also, I will just leave a couple of minutes at the end for some other related research that is ongoing, but not mature enough for prime time. Just to give a kind of introduction to the problem, we all have seen from news what is happening with the wildfires that are getting more severe, more intense, are reaching communities. We have seen the LA wildfires just this year. So this is a process in which we have this severity that is increasing. And obviously, there are multiple causes that are producing this effect. One is climate change that is producing conditions that are more that are guiding and making wildfires more severe. But also a long history of very aggressive suppression of wildfires that has increased the fuel available in many places here in California and in the US. And then a third tendency that is increase in construction, both homes, residential, but also infrastructure that are at the wild and urban interface. That region that is where construction and built environment intersects with the natural environment and vegetation, and these are the highest risk for wildfires. So one of the important data point that is often neglected is the relationship between the damage produced by wildfires on built environment and the direct consequences in terms of loss of life and loss of property. Very often we hear the intensity of wildfires described by acres burned. However, when you make that correlation, these are data for the last 20 years on the wildfires in California. When you see the correlation between loss of life and loss of property with the size of the wildfires, the acres burned, you find a correlation of about 40 to 50%, which is not a negligible correlation, but obviously is not explaining everything we want to really understand. However, When you do the same exercise with the number of houses that are destroyed by wildfires, you find a correlation that is almost one. So this kind of prompts us to say that the best return on investment, if we want to reduce the effect of wildfires on life losses and economic losses, is to act on our built environment and particularly on our houses, make them more resilient, harden them against wildfires. So with this in mind, we started developing a research trust that is on understanding how we can better protect our homes and our communities. As I introduced briefly in the outline, we are taking two different directions. On one side, we want to understand what is happening and how we can better represent it and model it for particularly for fires that are what they are typically called the conflagration fires. The fires where fires is really driven from homes that are burning and then are becoming the source of fire for nearby homes, and that's how communities are typically damaged. There is a need for assessment of these risks. Otherwise, it's very difficult to do science-based policy decisions. And what we have found is that there are a lot of agencies from the state, from local governments, from federal government that are collecting data for wildfire applications. But as we unfortunately all know, there is a lot of silos that are communicating very little among each other. And so these data sometimes are simply incompatible and cannot be used for multiple applications besides the one they were developed for. So we are working on this framework to leverage the data that exists in order to have a better understanding of wildfire risk. One of these objectives is the integration of heterogeneous data so that we can have empirical damage assessment to the build infrastructure, which is kind of our reality check for anything that needs to be used then for modeling. And at the same time, start to develop suitable distance metrics that can be used for damage assessment in a certain way, looking at a performance-based wildfire methodology that has to be developed. So what are all of these data sources that I was talking about? We have data that are collected before, during, and post fires. There are defensible space audits. There are Microsoft footprint that can give us information on the dimensions of different buildings, etc., etc., etc. We have also information on vegetation. And this is all collected before any fire event, before even knowing where a fire event will actually take place. And then there are data that are collected during the fire. So we know the location of the fire and we have information, for example, on the burn severity of the vegetation that is affected by the wildfire. And then post-fire, there are additional data collection done typically on field or with satellite images that can give us information on the damage that has been exerted on different types of buildings, homes, and structures. The issue is that all of these different data collections are done for different purposes by different agencies. So there is not really a protocol to have similar data that can be used for other applications, like, for example, understanding the risk associated with wildfires. Some of these data collections are also very expensive and dangerous because require physical presence of engineers, researchers, and other first responders after the fire has happened in a situation that typically is of distraction and thus complicated for data collection. So what is really happening here? Just to give an example from Tubbs Fire of the different types of data that we are trying to collect and put together. So on one side, we have the Microsoft information on the footprint that is given as polygons, so coordinates of corners. And these can give us the information on location of buildings and their size. We have then information that is given for the burn severity. The MTBS data set provides the fire perimeter and the burn severity with different types of data, different data types. And then we have the inspection, the damage inspection layer, which provides coordinate of buildings information on the characteristic of the buildings and the level of damage. And this is a little bit different depending if it is inside or outside the fire perimeter, because typically damage inspection is done only inside the fire perimeter. However, it is done at a time where the fire perimeter is not fully defined. And so there is some fuzzy region at the intersection between inside and outside the fire perimeter that needs to be adjusted in a certain way. So why there is this need for adjusting, in addition to the fact that we need to make homogeneous a set of heterogeneous data? That is because there are buildings that can be missed in some of the different layers of data that we are using. For example, typically damage inspections do not spend a lot of time to inspect buildings that were not damaged. Now, that is a problem if you want to understand hazards and risk, because there is a non-survival bias that is introduced. We get a lot of information on what did not work, but we would like to have information also on what did work and why that survived. So we need to recover that information in different ways. Also, perimeter buildings that are outside of the official perimeter of the wildfires are not inspected. However, they were exposed to wildfire risk nevertheless. And so that's another layer of information that we miss to understand why wildfires were stopped at that level or why those buildings were able to survive. This is, though, a problem that is obviously quite severe at the edge of the fire perimeter, where it's difficult to understand what is inside, what is outside, because that fire perimeter, again, is typically not fully defined when the damage inspection is happening. However, this happens also deep inside the fire perimeter, where very often damage inspections for buildings that were not damaged are simply not done for various reasons. One is cost, one is time, one is that we don't have access to buildings that are occupied by their owners unless the owners are there to give permission to do that. And so a lot of that information, again, is lost, but is necessary if we want to perform a rigorous analysis of risk. So we need to recover these data. And how do we do that? We need to go through several different steps that I'm going to try to describe here in what we are defining as a framework that provides us with a natural GIS tool to do this type of analysis. So we start with a Google Earth layer to have just the geographic characteristic of the location where the fire happened. And then we import into a GIS program or project the different layers that I have identified before. In particular, we want to have the information on location size of the different buildings and the damage inspection information that is available on all of the buildings that were lost or that were inspected even without damage. We also have to import the fire severity layer on the vegetation, which is giving us the information on the interaction between the built environment and existing vegetation. Also, all of these layers have different reference systems, so we need to rebuild all of the data into the same reference system so that they can actually be superposed. And then that's when we need to start accounting for unexpected buildings. We can use the Microsoft footprint to identify buildings that are not included in the damage inspection. And then that is relatively easy for buildings that are outside the fire perimeter. For the one that are inside the fire perimeter, we need to use different tools to avoid double representing and double counting buildings that are included or not included in the damage inspection when they are already available in the Microsoft footprint layer. So once we have homogenized everything and corrected the data to account for these unexpected buildings, we can start doing our calculations and math. And we are focused on two pieces of information. The distance from vegetation that has a high burn intensity and the distance from the closest burned structures. This selection is done because we started with the hypothesis that controlling factors on the intensity of the action of fire on buildings are really related to the distance from vegetation and from structures that are burning. And then, based on this information, we can assess the damage statistics, typically expressed in terms of percentage of destroyed buildings as a function of the distance from any of the sources of possible ignition. So let's now show what this looks like when applied to actual historical fires. We considered the two different fires, the camp fires of 2018 and the Tubbs fire of 2017. Some of the information on property loss, number of destroyed structures. Camp fire is still the largest in terms of number of buildings that were destroyed, although the fire in LA, the Eaton fire and the Palisade fires together probably are going to be very close once all of the information is collected. So we started by trying to understand what is going to be the effect of including or not including the uninspected buildings. When we look at the numbers of buildings that were inspected or non-inspected in these two fires, we see that with campfires, actually, there was a big effort of trying to capture all of the information also on undamaged buildings. In fact, we figured out that only 3% of the buildings that were within the perimeter were actually not inspected. However, this number is significantly larger for the Tubbs fire, where 27% of the buildings were uninspected. And so we expected to see small differences for the campfires, but significant difference for the Tubbs fire. And that was exactly what we obtained with our results. Here I'm presenting for the two fires the histograms of buildings at a given distance from high burn vegetation, and the number of buildings that are corresponding to that distance that were destroyed. Also, with the blue and black line, we are reporting the percentage of destroyed buildings at a given distance. This is simply the ratio between the number of destroyed buildings divided by the number of all of the buildings that were within a specified distance being from the vegetation that was at high burn distance or high burn intensity. And so you can see that in the campfire, these two curves, the blue one, which is the one based only on the damage inspection without the correction for uninspected buildings. The two curves are fundamentally similar. The difference is probably less than other uncertainties present in all of this data collection. And there is a expected decrease of the number of the percentage of buildings that are destroyed as we get farther away from the ignition source of vegetation. In the Tubbs fire, the blue line is fundamentally a constant, and that is because fundamentally all of the inspected buildings were the destroyed buildings, and so you don't get any information on the effect of distance from vegetation and buildings that were damaged by the wildfires. However, when we add the information on the uninspected buildings, then you can see that the ratio is actually significantly smaller because there is about a third of the buildings that were undamaged, even though they were at a specified distance from the vegetation. And so now we can start understanding also for the Tubbs fire that there is a dependence on the damage to the buildings with the distance, although it is not as clear as the one in campfire. And that tells us that just the distance from vegetation is not telling us the entire story. So that's why we also investigated the effect of distance from other burning structures to see if these fires could be really classified as conflagration fires more than as wildfires. And so also in this case, we found that the difference of the results in the methodology between including or not including uninspected buildings is relatively small for campfire, with a much stronger dependence of the survivability of buildings from the distance from other burning buildings. And we find the same type of effect, but much more magnified for Tubbs fire, where we start understanding that in the Tubbs fire, there is a strong driver that was the distance between different buildings in assessing if buildings were surviving or not. So now that we have a little bit of a better understanding of how to evaluate the relationship between survivability of a building and distance from ignition sources, we can also investigate other aspects in understanding what is driving this risk for the different buildings. One thing we focused on was the presence of outbuildings. Outbuildings are fundamentally non-habitable buildings with a dimension that is smaller than 120 square feet that are located on the property on a given parcel where there is another main building that is an habitable building. So the hypothesis here is that since outbuilding with this classification do not require the implementation of Chapter 7A requirements, those that are providing better resilience for buildings that are in the wild and urban interface. These buildings are much more prone to fire, at a much higher risk to fire than the main buildings. Now, this wouldn't be a problem if the only thing that you lose is the outbuilding. Yes, it's never nice to lose anything in a fire, but typically these are sheds that are used for just keeping materials and other things. So the risk to people and to the to life by themselves would be low. However, what we wanted to understand is if these had any effect on the survivability of the main building. And indeed, what we found is that if we consider only buildings that have no outbuilding, our relationship between the percentage of destroyed building for a given distance and the distance is even cleaner in showing the relationship that decreases in terms of risk as we get far away from vegetation that is burning. However, if we look at buildings that add outbuildings, we find out that actually we lose that relationship. So the driving force is no more vegetation that is burning, but as you can see on the right side, fundamentally the probability of burning, that is the percentage of destroyed building at a given distance, it practically becomes a constant. So it becomes independent on the distance from vegetation. And our hypothesis is that this is driven by the presence of the outbuilding that are burning first and becoming the main source that is controlling the burning of the main buildings. So this is just the representation of the main buildings, the outbuildings on the property, and then the end results that is fundamentally everything burned. Another application that we tried with our methodology is to see if we can identify the different ignition modes that are driving the loss of the different buildings. We know that there are three mechanisms with which fire can destroy a building. There is the most obvious one, that is contact fire, impinging flames from vegetation, nearby vegetation, or nearby buildings. Then there is radiant heat. This is typically driving for fires that are driven by large trees that are producing a lot of radiating heat and are too close to the buildings, but also radiating heat that can be produced by nearby buildings that are burning. And then there is ember attack of firebrand that are fundamentally driven by wind, can fly very long distances, and can kind of get all together in crevices or condensate around the surfaces of your building and produce ignition there, or penetrate through vents and other openings and then produce ignition of material inside the building. So there is no actual direct way to distinguish ignition modes. It's always something that has to be kind of evaluated a posteriori. And that is because it's simply unrealistic to have anybody to collect that data while the fire is ongoing, which would be the only way to have precise information on what produced the ignition for any specific buildings. What we are trying to do is, since we have this relationship between the survivability of buildings and the distance from vegetation ignition sources or structural ignition sources, we wanted to see if it is possible to define vegetation safety distance and the structure safety distance beyond which contact flame and radiant heat are no longer the driving force. So that anything that is coming from a larger distance than that is fundamentally produced by ember attack. And so we defined, using information available in the literature, these two distances, and classified the ignition modes in a very simple way as ignition produced by vegetation, radiant heat, or contact heat, whenever we were close enough to vegetation to have that ignition mode as possible, but far enough from structures so the structures were not contributing. And then vice versa, we had the structural radiant and contact ignition mode when we are far from vegetation but close to other burned structures. Then when we were close to both vegetation and structures that were burning, we had the combined radiant contact ignition mode. And when we are far from vegetation and other buildings, then the only remaining possibility is a non-radiant, non-contact ignition mode, which is fundamentally driven by embers. So how does these analysis look like for the campfire and for the tubs fire? It's really dividing the information into the 4 quadrants that correspond to the different types of ignition modes, which are here color-coded for a easier read of the information. And then we calculated 2 interesting measures to assess the contribution of the different ignition modes, but also their severity. So the first information is the ignition mode contribution. It's the number of buildings that are destroyed and belong to a given ignition mode divided by the total number of buildings that were destroyed. So this is telling us the relative contribution of different ignition modes to the destruction of buildings. The second information that we collected or calculated was the fraction of building destroyed within each ignition mode. This is given by the number of destroyed building by the ignition mode divided this time by the number of exposed building to that particular ignition mode. And so this is telling us how dangerous each ignition mode is in case a building is exposed to it. So this information is reported here with the 2 numbers that are associated to each of the 4 ignition modes. You can see that the radiant heat from vegetation has a small contribution in both the campfires and the tub fires. The radiant heat from structural ignition modes is an important component for the particular analysis that we are doing. The combined radiant is typically small because it's difficult for, or is rare, likely for a building to be close to both vegetation and buildings that are burning. And the non-radiant that can be exclusively reduced to embers is somewhere in between, is a significant contribution, but is in the order of 30% for these 2 fires. Now, the thing that I think is also interesting is the dangerousness of each of these fires. For all of the fires where there is radiant heat or contact flame, the percentage of buildings that are, the fraction of buildings that are destroyed within that ignition mode is always very high. It's of the order of 90+%. And the one for embers is a little bit lower, is of the order of 50%. So that means that really the distance between buildings and the distance of buildings from vegetation, which is something that is controlled in part, at least, by defensible spaces, is a very important component in ensuring the survivability of a given home and building. Naturally, this is something that we have attended for the first time. We are investigating better definitions of these safety distances, which are quite well defined for vegetation based on existing literature, which is also the one that has driven the control of the different defensible spaces zones in Chapter 7A. But the information on structural safety distance is not as well defined. And so right now we are trying to understand how much that will affect our results. So that's the information regarding the assessment of the risk. Now, what are we doing to reduce that risk? And our approach to that has been investigating different types of solutions, but the one that I've been focusing the most within my research group is the development of fire-resilient construction techniques that are also affordable and sustainable. And that is because we do have a need independently from wildfires for affordable and sustainable housing. And we want to have something that is more resilient to wildfires, because even in the best of the hypothesis of homes that are wooden made and follow Chapter 7A requirements, we are at the point where our survivability of that specific building is only about a flip of a coin. It has been estimated recent papers that the survivability of buildings that were pre-Chapter 7A is of the order of 10 to 12%. So 9 out of 10 buildings that are subjected and exposed to fire will burn. And more modern and Chapter 7A compliant buildings have a survivability that jumps up to 52%. However, I doubt that any homeowner would feel very well about knowing that the risk associated with their house to be lost during a wildfires is just a little bit better than a flip of a coin. So we do want to have better homes. And the particular research that we have been exploring is a modern version of a very ancient technology that is construction with earthen materials, for which, unfortunately, there is a lot of literature for materials development and sustainability, but much less information on the structural performance and particularly on the performance under wildfire conditions. And so what we want to do is investigate and demonstrate the wildfire resilient capabilities of this particular type of construction, quantify the additional mitigation that would be provided by using this type of construction, and in a certain way also promote earth block construction for wildfire risk mitigation. So what is earth block construction, or more generally earthen construction? Earthen construction is fundamentally recovering a nature-based solution for home building that is based on the use of soil and clay. This is a very ancient, probably the most ancient construction techniques after caverns that has been used for more than 10,000 years. Even now, about 30 to 50% of the world population, depending on the sources for this information, is currently living in earth-based dwelling, which are found all over the world. This map that is shown here with the orange on gray is indicating all of the different places where earthen construction is found across the globe. And on the right side of this slide, you can see some historical examples of earthen constructions that have been built centuries, if not millennia ago, and are still standing strong. So we have a lot of historical success, but not as much information. And also, there are different types of earthen construction that have been developed over the centuries. Comed, rammed earth, adobe. I'm not going to go into the details, but fundamentally, cob is a construction of walls using layer of slurry of soil that are put one over the other until the walls are built. Rammed earth is fundamentally soil that is compressed on two sides into a given position, and that's a big example of that is the Great Wall of China that is in many parts built using that technology. And adobe is probably the most known one where blocks and bricks are made with fundamentally clay and often natural fibers like straws. And then they are dried up under the sun after being lightly compressed by hand or by foot. Now, we are not advocating necessarily to use the historical technologies. We are actually trying to use modern engineering knowledge and modern science to engineer this technology in a way that can be used in parallel as a potential alternative to modern construction materials. This leads to some differences, for example, in the development of modern earth blocks that are compressed, stabilized, or compressed and stabilized. So what is this process? Compression is fundamentally a mechanical compression that compacts the soil, which is mixed with water, in order to increase the mechanical performance, the mechanical strength of the components. And chemical stabilization is the addition of a small amount of materials like cement and lime in order to provide more durability to environmental agents of this type of construction, as adobe tends to be significantly weak to environmental actions, and particularly water. And you can see here a couple of examples of modern constructions that are used, that are built using this technology. Here, just to give you an example of what it looks like, what an earth block looks like, you can see all of the different shapes that we are able to produce. On the top, you are seeing a little video of our first machine that we built in our lab. This was a manual machine, and as you can see, it's quite a laborious process to generate bricks using it. I have to say, I needed students that were typically physically well, very strong to be able to do that work. And the students weren't particularly excited to do it. So we ended up buying the machine that you see in the other picture in orange and yellow. That is an hydraulic Aurum 4000 machine where fundamentally you put the soil um, on this component here that carries it inside, and then the machine spits out the blocks. And now students are extremely excited to work on earth block construction because it's significantly easier. Also, with the manual machine, we were able to produce 30 to 40 blocks per hour. With the hydraulic machine and 3 people working to just pour the soil on the conveyor belt, we can produce 400 bricks per hour, which is a big difference when we try to build things. So why are we looking at these old technology? Why we are trying to reinvent an old technology? But first of all, because it is affordable and it is locally appropriate. You can find on this right side, we have the US Department of Agriculture classification of soil based on the components of clay, silt, and sand, where the red line is giving us the composition of the soil that fundamentally is ideal for earth block construction, where no additional um, stabilization is needed in terms of mechanical strength. And the yellowish line, dashed line, is indicating the range of soils that can be used with some stabilization. Now, the results of that is that fundamentally, unless you are building exactly at the end of big river, of the deltas of big rivers where the soil is too rich in organic components and too silty, you can find soil that is appropriate for use with earth and construction almost everywhere. Um, and the soil that is used is naturally resistant to a lot of the different things that can be a problem with wooden construction. They're resistant to fire, to mold, to rot, to pests, to termites, to pests, to termites. So they are naturally more resistant, inert than organic material like wood. Also, they are healthy and natural. On one side, they are a breathable material that is able to keep the relative indoor humidity always in the range between 40 and 60%. In fact, if the internal humidity is too high, this material is able to suck out the water, the vapor from the environment in order to bring it down to 60%. And if the indoor is too dry, it releases back this humidity, again bringing it above the 40%. It does not produce any volatile organic compound, which is a very important thing for any chemically sensitive people. Is also eco-efficient and sustainable. Given the high thermal mass, it allows, depending on the climate where it is used, a significant saving in heating and cooling, estimated between 30 and 70% when compared with the normal wooden construction. And then compared with the other masonry materials, which have similar properties for the other things that we have discussed, except the healthy humidity, they have a significantly smaller embodied energy, at least an order of magnitude less than bricks and concrete masonry units. And that is because the usage of cement is very low and the energy used to produce the bricks is extremely low, is only mechanical energy. In addition, recent research has shown that this material has a good resistance to hurricanes, tornadoes, to seismic actions when used in conjunction with internal reinforcement. And so the question now is, can we investigate if they perform well also for fire? Now, I don't want to say that everything is perfect. There are also challenges. One challenge is the material is a natural material, so typically has a higher variability of properties than other industrial materials. Also, it has typically a poor durability against wet climates, which typically requires the addition of lime and cement, which reduces a little bit the sustainability. So we need to know what is the right amount of cement or lime that needs to be added, not to produce material that is fundamentally greenwashed. And then it is a masonry material, so it's characterized by brittleness, which means that reaching the peak then produces an immediate reduction in the mechanical properties. It is also in the basic form that has been used through centuries, very labor intensive. However, even though I want to discuss all of these different things, we have found technical solutions for each of these problems with new technologies that use interlocking blocks to reduce labor, addition of fibers, natural fibers to improve the brittleness, and quality control to reduce the variability of the properties, as well as a proper life cycle analysis to quantify the right amount of cement or lime that needs to be used for a sustainable material. The major problem that we are still dealing with is really the widespread perception that earthen construction is a substandard choice. And this is mainly due to the poor performance of non-engineered earthen structures in other parts of the world, where, for example, in Turkey, they had a very poor performance under earthquake loads. However, even here, my point of view is that any material, when not properly engineered and designed, will perform poorly for loadings for which they were not designed. If you have structures in reinforced concrete or steel that are not properly designed for seismic actions, they will also perform poorly when they are subjected to that type of loading. So anyway, we went through all of this process, but I wanted to focus on the fire resilience. And here you can see a quick and dirty test we did with a propane torch at 3400 Fahrenheit between our earth block and the typical wood blocks that are used for construction of wood-based buildings. And you can see that fundamentally, as expected, the wood burns and the earth block, the only thing that you can see and observe is a little change of color. And in fact, then given this initial sanity check, we went and investigated the actual mechanical performance of this material when subjected to sustained high temperatures. We developed 60 specimens with natural soil that was collected from Paradise in California, which was the community completely destroyed by the Camp Fire of 2018. And then we tested these materials, these blocks at different, after exposing them at different temperatures. We left a group of blocks at room temperature, and then we subjected them to 200 Celsius, 400 Celsius, 600 Celsius, 800 Celsius, and 1000 Celsius. 1000 Celsius is 1832 Fahrenheit, which is kind of a upper limit for the typical temperature of wildfires that are only driven by vegetation. And so we tested them under different conditions. First of all, in flexure, to understand how this fire affects their brittleness. In compression under dry conditions, and in compression under wet conditions, which is typically the hardest test for this type of material. Here you can see some of the blocks with the different temperatures that were tested at the different temperatures. And here you can see how there is this change of color from the typical brownish color that is of the unfired clay brick. And then this change of color toward the reddish color until you can see this proceeds from the outside toward the inside until you reach at 1000 Celsius fundamentally a uniform red color. Which in hindsight is simply telling us that the unfired clay brick transformed into a fired clay brick, a normal fired clay brick. And so we did all our tests. We found that there is a slight reduction in the modulus of rupture from the flexure test. Although even at 1000 Celsius, we are remaining above the minimum requirement from the New Mexico Administrative Code, which is the only statewide code for construction using earth blocks and other earthen materials. For the dry compressive strength, fundamentally, we found a small but not statistically significant reduction in strength. And then for the wet compressive strength, actually, we observed a very significant increase in strength. And that is, again, because our unfired clay bricks are becoming now fired clay bricks, normal bricks, which are typically not weaker under wet conditions. I think, how much time do I have? I know we started about 10 minutes later. How much time do I have before I have to stop?
Uh, I would say like, oh, I don't know, 3 to 5 minutes so we can have some time for
Okay,
questions.
so I'm going to go quickly through this one. We also investigated what happens in the worst case scenario when the structure still burns. We wanted to understand emissions both in terms of greenhouse gases, but also in terms of PM 2.5 and other things that can be negative for human health. This is within a wider analysis of the life cycle, environmental life cycle for this type of constructions. In this presentation, I'm going to just talk about the emissions. And what we did was we took a natural house, single-family light frame wood house that has been rebuilt in Paradise. And then we analyze what happens when we build it without accounting for Chapter 7A by being compliant with Chapter 7A and then substituting wood with earthen blocks. And for all of these things, what we did was we tested the different construction materials in the lab to see the emissions per unit weight of the material, and then we scale it up to evaluate what is the emission that is coming from each square foot of or meter square of our buildings. And we combine that with the embodied energy for construction. So fundamentally, what we found is that the three types of construction starts more or less at the same level in terms of embodied energy. But then if they burn in the wildfires, as you would expect, earthen blocks do not produce a lot of emissions. And so all of the emissions are coming really from the content, while the emissions that are coming from the construction itself is quite significant. It's about 3 times the emission that is coming from the rest of the materials that are burning. And so just for conclusions, we developed this framework that we are using for developing wildfire fragility of different components of buildings. In this framework, we showed how to put together a heterogeneous data source in order to have a more accurate wildfire damage assessment of buildings. And we found that, as expected, the distance from vegetation and buildings correlate well with the survivability or with the losses in terms of destroyed buildings. Earthen masonry can be shown to be affordable, safe and sustainable for construction of houses and low-rise buildings. And our tests show that can also be used as a fire-resilient construction material that has a great potential to mitigate wildfire risk while at the same time promoting equitable economic development. Now, something really quick about the other ongoing research that, again, is not ready for prime time, but we are also working on developing a 3D printed version of these earthen materials As you can see, that's our first product in terms of 3D printed dirt and material with a very small auger. Now we are able to actually print out walls that are 6 feet wide by 6 feet tall. And then we need to be able to model this type of structures. And so we have developed a finite element micromodeling approach that allows us to predict pretty well deformation and load displacement responses of these type of walls, as well as the cracking shape in these walls. And then the most recent work that is still under construction is a wildfire testing facility that will allow us to test under wildfire condition entire buildings. And so we have a series of burners that are controlling the heat flux that is sent to the different structures. And here you can see on the right side the time lapse of the construction of our first benchmark, which is an earth block structure that will be tested under wildfires, probably at the end of this month or the beginning of the next one. Now with this one, finally I finish with the acknowledgements. Obviously, without funding, nothing can happen, but also without students and collaborators, nothing can happen. And if anybody wants to contact me, is interested in knowing more, this is my contact information. And with this, I'd like to thank you very much for your attention, and I'll be happy to respond to any question you may have. Thank you.
Thank you so much, Dr. Borbato. I would clap, but clapping on Zoom is weird. So we're going to just open it up for questions. For everybody in the audience, feel free to chime in. But if you're able to, in the react in the kind of bottom center, there's a raise hand react, just so that way we don't have people talking over each other. But otherwise, please feel free to ask questions.
Don't be shy.
Yeah, Dr. Patron, please.
All right, I just found the correct button. Thank you. Very nice presentation. I'll go first, hoping that we will have more questions from the students. But a couple of things that really caught my attention, and on the second part of your presentation, related to the earthing construction and materials. So you mentioned at some point that you found that using fibers and is really helping with, just overcoming a lot of limitations in terms of structural performance of these just materials. But I was wondering at the same time, which is, something to some extent that we would expect. Once we reinforce in different ways these materials, we improve performance. However, thinking that these fibers are usually plastic-based or polymers or steel-based, how is this going to affect then in turn your performance under fires? And so it's something you have looked into, you have, I'm sure, considered. And so what are your thoughts on that?
So we have been trying to get some funding to actually investigate that in details. We have used two different types of fibers without accounting for the effect of wildfires and fire. And the two types of fibers are fundamentally shredded plastic bottles and sugarcane bagasse fibers. This is because we started this investigation in Louisiana, where they had a lot of fibers from the sugarcane production. They didn't know what to do, and they were burning them, which I didn't think was a great idea at the time. And also they had the problem with the recycling plastic. And yes, they did perform very well in terms of mechanical properties post-peak, providing a significant ductility both in flexure and in compression. We do want to investigate what is happening in terms of the performance under fire. Probably I wouldn't use plastics because burning plastic is never a great idea. We have some indication from the COB world where they have used the light straw clay construction and tested that under fire. And fundamentally, the clay can have a sufficient thickness to protect the fibers in that case. We don't know if the dimension of the blocks would have the same type of protective effect. Maybe not, but it's just really a question of getting the funding to put a student to do that type of investigation at this point.
All right, thank you. I have a couple more, but I see other hands raised, so I will just let other people ask questions. Thank you.
Go ahead, Greg.
Thank you very much. I have experience with defensible space, and I'm curious, in your fragility model, you looked at the distance to vegetation. Will you or did you consider that type of vegetation, ground versus crown, the fueling type? Obviously, crown much hotter than, ground. Did you consider that, or will you?
So we are using the maps for the intensity of the burn that can be layered with the maps of the vegetation before the burn. And what we are trying to do is to find a more physics-based parameter that can be used. For example, heat flux that is connected with the type of vegetation, but you don't need to have that type of granularity on understanding what is each individual tree. Also because the typical maps are a 30 by 30 meters grid, which doesn't allow to really understand more than the general classification. And so if we can relate the general classification with a measure of heat flux, that will also make our physical testing easier because we can control heat flux or parameters that are related to temperature much better than generating exactly the vegetation that is happening. And also that would make it kind of more homogeneous between the effect of buildings and vegetation, because at that time we have one physical parameter that can describe both. So we are looking into it, and there is a student that is actually doing exactly that, but getting the passage from vegetation to heat flux or to other physical parameters apparently is not a very straightforward passage. In at least in realistic conditions or real world conditions. There is quite some literature on heat flux for different types of vegetations. There is almost nothing for structural components, and that's another thing that we are trying to work on. So it's definitely very important. This is a great question, and this is definitely something we are looking at.
Thank you very much.
And also we are looking at how to better include the information on the defensible space, because the maps on vegetation burns don't really give enough information to assess if a given building had a proper or non-proper defensible space. And so we are trying to use vision-driven methods, typically artificial intelligence, machine learning, to try to look at the maps before fire, the images before fire, to have a better assessment of what was the condition of the supposedly existing defensible space. That's another important component that we are trying to crack, but it's going to be, it is something we expect to have a very large effect.
Dr. Patron, would you like to ask another question or two while the rest of us consider our questions?
Yeah, sure. So I can go ahead. Well, one other I have is related to what I was just asking earlier. So is your kind of like longer term just a vision to go back to like brick-based construction with this new material, or based on what you were just showing with the 3D printer? So what's your kind of way to look at these new materials and new shapes? Because I see that you also work on this finite element model to kind of represent the response under seismic, potentially wind loads and a combination of gravity. So but what's your like vision in terms of how to use this sort of old-fashioned materials with new shapes potentially?
Yes, so the current direction we are taking is to go back to a brick-based construction, but without mortar. So we are developing an interlocking mortarless post-tensioned system that is significantly faster to construct. And if you want to visualize it, it's fundamentally giant Lego blocks that are interlocking to each other. And then they have holes inside with internal reinforcement that is post-tensioned just by turning bolts, keeping everything together whenever there is a lateral load and avoiding kind of a out of plane movement that would be otherwise damaging to the material, but also compressing everything so that without the need for mortar, you have still a wall that is impermeable to outside agents. So this is the current version that we are trying to investigate because all of the technology is readily available, and we have done a feasibility study with this approach, and we have about a 50% reduction in labor costs, which makes it actually with slightly less expensive of wooden construction in places like Louisiana, and slightly more expensive than wooden construction in places like California, just because of the difference in labor cost. But fundamentally, very close to wooden construction, but with much better performance under all of the different actions of flood, wind, hurricane, and fire, and still very good performance in terms of seismic loads due to the internal reinforcement. Now, 3D printing is something that many people present as the solution to everything, and I typically don't believe in a single silver bullet that resolves all of the problems. I see applications where 3D printing makes a lot of sense, where it's difficult to reach them, places where labor is really difficult to have or too expensive, and these kind of things. I don't know if it can become a solution for everything, but I think it has a space on where it also can be used. Although, again, I don't see it as the first selection for large scale application. I think something a little bit simpler that still uses modern engineering, but doesn't try to remove the human part of it completely, is probably has a higher chance of success for a more widespread utilization of this technology.
Okay, perfect. Thank you. We may need at some point to have probably an offline discussion, because we are working on a concept, this Lego-like concept of assembling your bricks. We are working on slightly larger components, but we're also post-tensioning. So it would be interesting maybe to have an offline discussion on the way you are addressing and we are addressing similar issues. In our cases for the Army, for gap crossings, but I see a lot of analogies. So it's interesting to know that you're working on a similar concept.
Love to talk about it.
given this, I want to be respectful of everybody's time, so let's do like one more question and then any other things we could do with offline discussions with the presenter. So yeah, does anybody have any last questions?
Fortunately, our students have this kind of, hard stop at 1, and so we ran a
Oh
bit
yeah.
long today, and so most of them had to leave.
Mhm. Yes, and I know Dr. Borbata, there was a previous professor that wanted to stay after, but I think they also had another stop at about 1:15, unfortunately. So yeah, it happens. You know how it is. Everybody's busy.
Oh yeah. Anyway,
Okay.
if there are no other questions,
Mhm.
it was a pleasure being here, and
Mhm.
thank you again for inviting me. And
Mhm.
look forward to opportunities for talking about our research, maybe collaborations, and all of that.
Yeah. Yeah.
Definitely.
Thank you so much, Dr.
You.
Borbado, and everyone else for joining.